My name is Max Körbecher. I'm founder of Liquid Reply, being partner there, or what I like to say, I go to the customers, drink coffee, and talk with them about technologies as Kubernetes, open source, and stuff like that. That's my day job. That's where I practically get the cat food for my little fat cat. And if I'm not doing that, do a lot of stuff within the open source space. I was 3 years contributing to Kubernetes, mainly in the release process. Nowadays, more like on the organizational side. I started kicking off the technical advisory group for environmental sustainability. I got elected or nominated for being a CNCF ambassador, and also recently joined the Linux Foundation Europe as an advisory board member. So practically all day long I'm sitting computer or drinking coffee with customers and sitting computer, something like that. Today we are talking, or I'm talking, about sustainability. And sustainability is, for most of us, actually a topic which is way more older than we are. For some, this topic might be very annoying, painful, right? Who hates it to hear all the time, oh, you need to be more sustainable, be good with your trash, don't drive the biggest car, maybe you should not fly so often, and so on and so forth. So it's an ever-presenting topic. But it's getting very, very relevant to act on it. Because, in fact, theoretically, we fucked it up. Because last week, it was the first time that we could measure globally that the overall heat was increased by 1.5%. And if you remember about all the reports which stated if we reach 1.5, we're going to have a very, very big problem. And that means this will happen now more often, day by day. Sometimes we will have weeks, we will have months, and then it will be our everyday. That means very big floodings, tornadoes, wildfires, whatsoever. We have to deal with it. This is what we cannot return. However, the question is how worse we want to that it gets, because there is no limit on the top. And that's what we need to prevent. And that's why we talk about sustainability, because ICT, or IT in itself, is as harmful as the aviation industry. It is as harmful as the whole cement industry, which some people don't know, but building a building is so unfriendly to the environment. It would be better if we would build just something else, wooden logs. And even that would be bad because we need to chop the trees. So maybe we should dig just really a hole and sit in it, and then that would be the best approach which we can take. Now, looking at these numbers, they are heavily inaccurate. Some forecasts practically say, until next year, ICT consumes 4% of the global energy. There are other forecasts and research which say, it will be 12%. And other forecasts think that within 2030, it will be around 20% that the whole ICT infrastructure will consume the energy. Why this is so heavy to translate to the CO2 footprint is because, well, it continuously changes. The only good thing which we have on global warming is that we have more wind and sometimes a little bit more sun, so we can maybe power a little bit more the energy change, but overall it doesn't help that much. Key driver for all of these things are data distribution, digitalization. Who gets actually a fear of missing out looking at AI? Right, it's like popping up continuously everywhere. AI here, AI there, everyone starts LLMs and blah, blah, blah. Yeah, thanks, that's a very big driver because everyone now wants to download tons of data and train them on machines and have no idea what they're doing, and power with this change even more. And last but not least, as said, carbons are everywhere. And I will talk about this paradox later a little bit because it's actually quite funny. Whatever we do, in the first step, we always will cause more carbons, which is stupid. So the biggest problem which we have in the ICT is that we missing the link between the power consumption of infrastructure or applications down to what is the actual energy mix. And this link is sometimes so poor that even the best cloud providers utilize just the data from the past year, which is not that helpful. I give you an example. In my past history, I was working 4.5 years for an energy utility company. Therefore, I know that every power plant on this planet is going every 5 to 6 years for at least 1 year in revision, aka it shuts down. Means if I shift my workload to Sweden, or Helsinki, which is most of the time water and nuclear power plants, that's why they are green, going shut down, they are not ramping up the other power plants because they need some buffer. They will buy dirty energy from other countries. Because, for example, Germany is quite close. We make everything now with gas and brown coal and other stuff, which is all very wastely. But they need to buy it if they go into revision. If you look just on the data from the last year, everything looks good, looks green. But if you put 1 or 2 nuclear power plants into revision, that's not anymore the truth. And this is going to happen in every country continuously, step by step. So, and then, comes solar and wind and all the other stuff. So there's a lot of change in it. And this is what you actually want to know, right? Where I right now should put my application that it's not that harmful as if I just run it somewhere in the middle of Germany where there's like 15 brown coal power plants around it. So this link we somehow need to get. And if I would be here last year, I could not really talk at anything in the following slides about it, because it was not there. And that's quite interesting. And of course we need to talk about Kubernetes, but I actually hate it if people represent this as Kubernetes, because it's not Kubernetes. Kubernetes is not a tanker, right? Kubernetes is more like a very nice Lego platform, where you can put bricks together and link things together. This picture reminds me of the slides from Thomas, like with a cluster mesh and having things connected. This is what Kubernetes can provide. And the real superpower is about to setting the things by providing a unified API. Because it's getting difficult. We have tons of different cloud providers. We have edge providers which are popping up. We have private cloud. We have bare metal. If you want to build for everything of these topics our own solution, we will be never done. That's an impossible mission. And there's one more thing which I need to tell you about. Besides all this complexity which we have different categories of CO2 which we cause. Scope 1 is everything what is direct, right? So you drove here, that would be a scope 1. Scope 2 is everything what is indirect. Who has something running in the cloud? Good, you're all happy scope 2 customers. And indirectly with that, also scope 3 customers. We differentiate here between the upstream and the downstream, like getting rid of the trash which we produce, old servers, and all the cool new stuff, ARM-based servers whatsoever, which we have to produce and ship to the data centers. Now, the biggest thing which we can do, because I'm not a data center guy, I have no influence on scope 3. What I can do is optimize scope 2. Because if I reduce the demand for hardware, someone doesn't need to produce so much hardware. This is what I can do with my direct impact. Maybe in the next life I'm going to build data centers. Then I will tackle more the scope 3 problem. But this is what we can do for all who is working in a cloud-native environment to really provide some change. So what we can do. This is like, I would say, the most typical stack which most of us know. We have somewhere a hypervisor, a little bit Kubernetes, some containers, and tons of other stuff running. What we can do is to optimize the image. This is old but gold, right? Keep the images small because you also want to save some storage, should be faster, and so on. We should take a look that we put actually a lot of containers into the same cluster and the same nodes, scale the containers to 0 if you don't need it, or even scale the whole clusters down. And recent trends going, for example, to ARM. The thing is, for me, this is actually greenwashing, because a lot of people use this and say like, oh, look, I do all of these things, and that's why I start doing sustainable IT. This is not wrong, but it's also not right, because you optimize things blindfoldly. You know it will have an impact because you shut things down, but you cannot provide the evidence of how big is the impact and if it have really helped. There was a recent study, for example, about ARM servers, that they are not that efficient with every programming language, not that efficient with every kind of program, and sometimes can even slow down your processing. For sure, these are edge cases, right? But you need to be aware of it because you need to be selecting precisely where to put what. What we have to do is maybe a future without containers. Why? Well, because the software itself is typically very, very small. I'm a big fanboy of WebAssembly, for example. So shipping around a megabyte or 2 megabyte big container, that would be awesome. Just needs 50 milliseconds to get started up. You can store it practically everywhere. Sounds like a decent future. Scheduling based on carbon data. That would be so awesome. Now we cannot do it, but we're working on it. And scale based on scale and schedule based on carbon data itself together. Maybe we change the architectures. Maybe we have to implement new architectures which supports these changes and help us to shut down unneeded resources. And the biggest problem, improve the power management. The power management of server is like the big mystery in this universe. If you set a server into echo mode, it doesn't mean that it saves energy, it just means that it cannot scale up. You put back practically, I don't know, something on top of it. But it will always use energy until you completely shut it down. By the way, that's a good reason to go to a cloud provider, because if you really have some workload which idle and is not doing anything, the server is almost getting shut down completely. So we have a couple of categories what we can do actually to optimize. And the quite relevant story here is that from going top to down, we started the greenwashing area and coming to all the steps which we currently develop and getting better to, with a real precise target to optimize what we actually do to reduce CO2 footprint. Scale, reduce, right size is written in every cloud provider's framework. Right? You need to do your infrastructure right. The big challenge is that with on the fingertips of yourself, and depending on how big is the deposit on your credit card, you can more or less scale infinitely. But we should rethink this. Yes, we can scale infinitely, but we should not scale continuously infinitely. We see here also some recent very interesting developments. Carpenter, for example. It's therefore measure and practically matching the power consumption of an application within a Kubernetes cluster. Yet difficult to set up on some points, but we're getting better there. Open source project, very cool to go. KubeGreen helps us to shut down idling systems. Or Kida, just like 2-3 weeks ago, released a blog post about custom metrics, and therefore also being enabled now to get triggered by power or CO2 data. And this is an initiative because out of the discussion which we had in the technical advisory group with Kida. So we start moving into the open source space and giving ideas where we can start utilizing the tools which are out there and give them just a new kind of data set to act on it. These are two examples. On the top left, you see, for example, the information you can get out of Kepler. You see there roughly the watt-hour per application which is running. And on the lower part, you see Scaphandra. Scaphandra is more relevant if you have virtual machine workload. Then Scaphandra performs a little bit better, gives you more relevant information. The good thing is both give you the relevant output which you need to think about and optimize your system. So you know exactly how much power from the CPU, memory, and storage an application requires. Plus you know how much energy the whole system requires. And so you can more or less precisely identify and start optimizing on the software. The other part, and that's always a little bit challenging, is to combine this with the CO2. First, you need to know where the hell is my application running. Most of the time it's easy. It's in Frankfurt, it's in Zurich, it's in Helsinki. But then you need to find out how is the energy mix at the moment. And this is getting difficult because what you get from the cloud provider is old, outdated, and from last year. What you want to have is very accurate data. You can see here one from Great Britain, 312 grams CO2 equivalent per watt hour. It's not good, it's not bad, right? I come from Germany. You see it's a little bit more browner. If you go top to the Scandinavian countries, it's a little bit more greener, right? So you can do obviously something by shifting your application. We come later to some myths where we clarify this, but the energy map and, for example, WattTime API provides you this information quite precisely. In which region do you have currently which kind of energy mix? And this is what you need to put together. We don't have this automatically yet, But I believe if we meet here next year again, I hopefully can tell you a totally new story and can tell you, hey people, look, awesome tool, it matches all the stuff together. Now you just say what you want to achieve and it's doing it by itself. The other thing is changing hardware. I told you about ARM. It has for most of the stuff a very good impact. What we also see, WebAssembly, sorry, I'm a little bit fanboy on this. But it makes sense because it's reduced a lot of the workload, a lot of the data which needs to be transmitted to execute your application. And it always scales to 0. It does not run if it doesn't have to execute something. And it can be so fast spinned up that you realistically can shut it down. And we can talk about green regions. Luckily, we're today here at Google, and Google Cloud does this quite fantastic. You have indicators on the Google Cloud, which region are greener than the others. And you even get it per server type, for example. So you can choose per default, like, hey, I would like to go, let's say Helsinki, use this one specific server type. They are marked as being greener than the other areas. And in the Carbon dashboard, you can even find out why it is like this, right? Because it's maybe of the server type, maybe because of the energy mix, maybe because of the passive cooling of the data center, stuff like that. I'm ahead of myself. WebAssembly, ladies and gentlemen. Adjusting system architecture is also another thing. And this is something where we currently see also a lot of movements. The Green Software Foundation here, for example, started to build a catalog, mainly for web applications, AI, and the cloud, where they put down patterns for how do I optimize my system setup to not to be too harmful for the environment, and what is the exact impact. The Green Software Foundation also did this with a specification called SCI, or Software Carbon Intensity, where they describe this in their catalog, how is the impact on these different variables within the SCI specification. So I can understand, is it something which reduces, for example, the energy? Is it something which has impact on the embodied carbons, or what so on? It's a good starting point, but it also needs contribution from us. And I believe for some areas, there are experts out there which have better ideas how we can save some of the energy needed. And we need to be more smarter with data. Who is running a global data mesh? Damn it. Sorry. We built for one of our customers a huge, large data mesh around the globe. Practically, it runs on every continent in a couple of data centers, being connected, transmitting data from A to B whenever someone needs something. That's cool, but it's incredible dump, because we're transmitting tons of terabytes of data around the globe, where it would be way more easier to move the application with a few hundred megabytes to the location, do the processing, and just get the results. We're working on it, that this was happening, but if sustainability is not your priority number one, you maybe do not get there, right? If you're a data scientist and you want to have your data somewhere, if you're a BI analyst, whatsoever, you want to have your large data lakes, I think this is going to be the past. Which is quite funny, because we spent the last 5 years on building big data lakes, right? But this is really not the sustainable future of it, because it's very costly in terms of energy. And last but not least, optimizing software. Programming languages, algorithms, whatsoever. This is the biggest problem which we have, because there's no real study around it. What is the best algorithm for X, Y, Z? This is solved. But who remembers from his studies or whatsoever in which case I better use this kind of sorting or this kind of search? I don't. Well, I was also very bad in programming, but I still don't remember it. The funny thing is, there's this study. Who have seen it? Perfect, please forget it, it's bullshit. Well, it's not bullshit itself, right? It has some reasoning, and like 6 years back when this happening, and the programming language were 1 year old, this was for sure a reason outcome. But we also know that many of those programming languages which are listed have improved in their performance over the last 6 years, sometimes drastically. So it's not that easy to sit down and say like, oh, everyone writes now software again in C and Rust, and please forget about Python and TypeScript because it's X amount worse. Yes, maybe it's still like this, but the gap gets closer. And it doesn't make sense to reinvent the whole application and rewrite everything in new programming languages. But if I have the possibility to write something in a new programming language, I still can consider what is the best Pareto optimum which I can get, right? And then I found maybe something which makes more sense in the future. Welcome to MAS lecture number 1. This is the software carbon intensity specification. And because I found this very clumsy, I would like to give you more an example of it. We see in the middle the formula and filling this out with some information. E stands for the energy, which in this case a Prometheus server running in the 3-node cluster requires per watt hour, which is 0.35. I is the carbon emission. It's on the left corner with 0.32 grams of CO2 equivalent per watt hour. I know it's super complicated and it can get more complicated. This is because it's running in Germany. If you would move to Sweden, it's already just 0.2. So there's a good amount of optimization which I can do here. This both information together give me already an idea how big is the CO2 footprint of my application itself. What we then need is also the embodied carbon emissions. And the embodied carbon emissions is what is baked into your server which you're using. And they make up to 85% of the whole carbon emission a server over its whole lifetime will have put into the world. That's why it's important, for example, to think about how we can run servers longer, because the set amount of carbon emissions then distributes over time and lowers overall the carbon emission per application. In this case, we have just used a very generic Dell server running over, I think, 4 or 5 years, which boils down to 122 grams CO2 per watt hour. And because the Prometheus server just uses 10% from all the applications on the server for running, I multiply it with 0.1. And then, this is very important part, we need to know the scale factor. The scale factor is per watt, not watt, but per watt with H. This number is scaling. Is it the amount of user? Is it the amount of request? Is it something else? It can be very complicated, because the truth is, I cannot say like, oh, every 10 user it's like spiking. You never see stairs in your application. Maybe it's about a number of requests per user over time, blah, blah, blah. So if you put this all together, and we use here just the number of nodes because it was the most easiest one for me, we come to that the server uses 4.01 grams CO2 per watt hour. That doesn't sound so much, 4 grams. You even would not feel it in your hand, right? If you run this service 1 year, you can drive around 400 kilometers with it with your car. And this is just a little Prometheus server running on a very little unneeded server just for measuring it with 3 nodes. 400 kilometers with a car. That's quite a lot for this little application, right? And how many Prometheus servers we have out there? Tons. Everywhere. So it's horrible. We need to optimize this. So why do we need the SCI is to identify if moving to another region is really helpful. We need to think about to optimize the software, and then with the SCI we have always a KPI to say, okay, it can get better, we can optimize here. And we can combine the SCIs to identify for a whole system how heavy it is, and find out if we change the architecture of it, if we change databases or message streaming configurations, if this has a positive impact. So an SCI is more here to help you. And we need to take a look on our processes. Because not every one of us is Google. There is no need on this planet to build every commit which you do to GitHub or somewhere else. And we also need to optimize the whole CI/CD pipeline. It's something where we can get out a lot of unneeded builds, which is unneeded data, which is unneeded runtime of a server. And what we have started with one of our customers, for example, we have shut down the GitHub Actions runners. Obviously, it's a good step, right? I don't need to have the runner 24/7 running. So we shut it down in the evening, night, and weekend, and everything is fine. So we reduce here in the build process. Means also on the other hand side, we can just do daily builds. We don't have a nightly build anymore because no one on this planet needs actually every night a build. It doesn't make sense, only if you really have to test something. All right, because I'm running out of time, just very short, some myths which I have to bust. Time shift jobs. Someone needs to make first a research study on this one because the benefits are typically not that much given because you do not have a benefit out of it. You will not recognize the impact practically because the energy is most of the time in a more or less kind of stable way. Relocation and following the sun. Well, think about the part of being smart with data. Also that needs to be calculated end to end before it makes sense. And optimize for costs will for sure optimize also your CO2 footprint. I'm also doing FinOps. I can tell you that fits, but it doesn't need to be. I can also implement way more heavier architectures, which are slower, need maybe a little bit more money, but have way less impact on the environment. For example, running on old hardware and migrating to that. And with that, and because of more or less running out of time, we have sustainability paradoxon, which practically says you should run your application, your Kubernetes cluster, on old hardware as long as possible. And Kubernetes is very predestinated for it. It's a perfect solution to run applications in an unsecure, unstable environment. Because if one of the servers is blowing up, I don't care because Kubernetes shifts somewhere else. Perfect. The paradoxon behind it is you should actually use better servers, ARM, which are produced in a way healthier way with less water waste and less other heavy chemicals which put out there, and which are more energy efficient in solving all your mathematical questions. So what is the right way? I don't know, but you need to decide, and you can decide, and you can find out for yourself what is the right way in implementing it. If you want to join us and if you have great ideas, we have a Slack channel for the technical advisory group for environmental sustainability, and a lot of ideas running on GitHub where we work with other open source projects together. Or, yes, old but gold, there's a mailing list. Also, I don't like mailing because it's, again, very harmful for the environment because you nearly can send a letter if you send also an email. And with that, thank you very much, and I hope you have some questions.
Thank you very much. Questions?
Don't be shy.
Time for one question. The first one is the hardest always. Oh, no.
Do you really believe that without economic incentives, you can really change anything with regards to making sustainability putting it in the forefront?
Yes, because we're working with a couple of customers together who are just asking us for that. They don't care about how expensive it is. Right? The good news is when you optimize for reducing the power consumption, you will save costs. The only question is, will it make sense over the time period? Right? Because you have to ramp up a project team, for example, but for sure it will. And the other part is how big is the gap which you really provide. The thing is with right sizing, cutting down and servers and whatsoever, you do already a very, very large step. Typically we say blindfolded going into any kind of optimization problem for a customer, I can cut you down 25% of everything. All right? The very funny thing is that the amount of money which we're going to save is comparably low to the amount of CO2 footprint which we are going to release. on this part. Because switches to ARM servers, for example, is very huge. Reducing HA availability of databases, for example, has also a very drastic impact. And to change the data flow is also an incredible helpful lever here. And yeah, this gives some economic benefits typically with it.
Thank you very much. I have to interrupt here to make our break not too short. So after a round of applause first.